Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about directional fields and Euler's method. So both of the topics that we're going to be covering today deal with approximations to initial value problems. We have not yet learned how to solve initial value problems, but these will kind of give us an insight as to what we're looking for and what the answers are going to be to them. So again, both these techniques are approximations for initial value problems. So let's start off with directional fields. Firstly, let's suppose that we're asked to find the solution and graph the solution to the initial value problem of this, that y prime is equal to x plus y, where y of 0 is equal to 1. Right? We kind of don't know how to graph the solution to this problem because, well, we don't have an equation of a line to draw. However, what we do know is that the slope right here, so the slope is equal to the sum of the x and y coordinates, right? This is just another way of writing what was up here. So what we can do with this is we can draw out all the slopes and then from there match up where y of 0 is equal to 1. Now essentially how that'll go is we would have to kind of treat this y prime right here as a multivariable function. It basically would take in x and y as inputs, and then it would tell us the slope of a line basically at a certain x and y like coordinate pair. So we can think of almost as like y prime is equal to a function in taking both x and y, and then this function right here would yield us the slope at that coordinate pair x, y. So if we were to sketch multiple like little line segments using this formula right here, we would basically end up getting a directional field or a slope field. Now I'm going to show you how that goes right now. So here's what a slope field or a directional field would look like. Obviously I've not hand drawn this because, well, as you can see, there's a lot of segments there. So I have used a graphing calculator for it, but you can also compute it by hand. So basically what all these segments represent is the actual slope at those points. So it doesn't really draw a graph like we're used to, where we're giving a function like an x value and then it sort of shows us like a graph. This is going to be a bunch of line segments basically from a graph that would have been. We can see these little patterns kind of emerging. We can see that, okay, well, across this diagonal right here, well, the slope is constantly, like the line is constantly horizontal. And what does that mean? Well, that means that the slope is 0. And that makes sense, right? Because, well, let's choose this line right here, right? The x coordinate is going to be minus 6, and then the y is going to be 6 as well. And as we can see, the slope is given by the sum of those coordinates, and that would mean that the slope is 0. And that corresponds to that horizontal line. And we can see that it's happening everywhere where the x coordinate and the y coordinate are opposites of each other. What we can also see here is that the slope, like to the left of that 0, well, that's -1. And again, why does that make sense? Because going over 1 unit left would mean that the x coordinate is going to be less than the y coordinate by exactly 1. So in this case, this coordinate right here is -7 and 6, meaning that if we sum those two up, well, it's going to yield us -1. And again, we can see that this is constant all across this line right here. Obviously, to the right of here, well, the slope should be +1, because in this case, the x coordinate is going to be the sum between the x coordinate and the y coordinate, in this case, would be positive. So the x coordinate would be -5 and y would be 6. And then we would get a +1, meaning the slope at that point is going to be 1. Now, if we continue this process basically of taking any random coordinate, like let's say here, well, this coordinate is going to be 3 and 2. That means the sum of that is 5. That means the slope at that point is 5. If we keep drawing these slopes right here, eventually what we're going to get is this full directional field, or sometimes we call it a slope field. And this will kind of show you how the lines or the family of functions for the solution curve. The problem was asking us to graph this initial value problem right here. And now what we can do is we can label, because it needs to match this condition right here where y of 0 equals 1. We need to find that point. And that point is somewhere alongside here. What we could see is that all of these lines sort of follow this shape where they go like that, right? first they go down here, and then once they hit over here, well, all of a sudden they're kind of all booted upward. And a likely one to pass through this point as well would be something like this. Actually, I'm going to draw it in red so it's kind of more visible, but it would likely be something like that. And maybe that is our approximation for this initial value problem. So that's essentially all a directional field is. It will kind of draw out the slopes at each coordinate pair, and then from there we can kind of see where the lines are tilting towards, and we can make a slight approximation as to the solution for the initial value problem. So now moving on to Euler's method. Before in directional fields we saw that we can kind of get a little approximation of what the sketch might look like for the solution curve. However, it didn't really give us a numerical value. So what the Euler's method does is it tries to give us this numerical value. And we basically try and approximate that curve by using a series of linear approximations on certain intervals to help us approximate that function. And obviously, if we have a function that is kind of the approximation of that, of the solution curve, well, then we can use the approximation function to figure out the value at a given point. Now, I'm going to kind of show you visually what we are going to be doing using the Euler's method. So I've kind of drawn it out here, but this is kind of Euler's method in action. Basically, let's assume that we have this green curve right here, and it's the solution curve, right? So this is the actual curve, the actual solution to the differential equation, or the initial value problem, actually, I should say. And then we have this red curve, which is basically the approximation at a certain value. Let's say it's the approximation at here. And obviously it's going to be really, really off, well, because we have a really high step pattern right here. And basically that step tells us how often we are going to recompute the slope of that approximation. Obviously, the less we recompute it, the worse off the approximation is. So now if we look over here, well, now we've taken a step of 0.5, meaning we're going to recompute twice. And as you can see now, it's starting to look a little closer. And you can almost guess that if we were to take a higher step interval, that we would basically be getting closer and closer to the real function. We'd be approximating a lot better. Now, the way we solve these problems, these approximation problems using Euler's method, is actually pretty simple. There's basically just like 4 steps and then a chart. But basically what we want to do is we want to start with the initial condition. And after we have started with the initial condition, we want to find the tangent at that initial condition. And basically step number 2 is essentially drawing that line right there, that approximation. Now for step number 3, we want to recompute and basically correct it or get closer to the line or get a better approximation. So we say that x1 is equal to x0 plus the step, right? The new x value, we were here, we're just going to add on the step value, and we're going to end up here. And this, in a sense, is kind of like ending the line and making the correction. And lastly, all we want to do is we want to continue computing until we reach our desired value. So these are the 4 steps we need to keep in mind. And now I'm going to show you the chart. Basically lays it out really nicely for us how we can kind of apply Euler's method. So I'm going to go ahead and draw it out real quick. There is the chart that we're going to use to compute Euler's method for an initial value problem. And essentially all we're going to do is the same stuff that we've listed off. So we start off with x0 and y0, and then here's obviously that slope at that initial condition. And we basically use these 3 right here to compute the equation of the line. And the equation of the line, well, that's given by the slope times x plus b, right? Obviously the line is given as y equals mx plus b. M we have, x we have, y we have. So we simply just compute b and find the equation of the line. Now we kind of compute the next value of x, and all we do is this h right here is the step pattern. So again, we're going to find this next x, and then we want to compute the y value of where that next x would be, basically finding the coordinate of where we're going to start this new line. And then we start the process all over again. Now that we have this next x and next y, Well, we find the slope at that x and y, we find the equation of the line on that little interval, and then we find our next x. And the next x in this case, well, that would be x1 plus h. And again, we recompute the y value at that x value. And we basically keep doing that until we get down to x and minus 1 and then y and minus 1. And the reason for that is because, well, the next x and the next y are going to be computed at this step, and this would be the value that we're actually asked to approximate. So I'm going to give you a brief example as to how we can apply this to a question that would need to use Euler's method. So here is the example that we're given, and it asks us to approximate the initial value problem. Right here, the differential equation is given by y prime equals y. The initial condition is that y of 0 equals 1, and we are asked to find what the y of 1 is using a step of 0.5. So again, I'm going to go ahead and set up this table real quick. So there we go. I have set up the table. I'm actually just going to make these a little longer, but step number 1 of the process tells us to start with our initial condition. Basically, the initial condition is right here, and it tells us that when x is equal to 0, y is equal to 1. So we're going to label x is equal to 0, y is equal to 1. What is y prime? Well, y prime is given by this equation right here, and the equation states that y prime is equal to y. In this case, y equals 1 right here, so that means y prime is also going to be 1. Now for the equation of the line. We know that the equation of the line is given by y equals mx plus b. So we have x is equal to 0. Actually, we'll start with y. Y is equal to 1. M, meaning the slope, is given by 1. The x-coordinate is going to be 0 and then plus b. So we get that b equals 1, meaning that the equation of the line is y equals to 1x plus 1. So y equals to x plus 1. And now we can compute the next x. Well, what is the next x? The next x value is the current x value plus the step pattern, or the step value. In this case, the step value is 0.5. So it's going to be 0 plus 0.5, which is equal to 0.5. And now what is the next y? Well, the next y can be found by using the equation of the line. If we have our x value, all we got to do is plug it in, and we get that y of 0.5 is equal to 1.5. So now that we have our next x and next y, all we need to do is simply put them over here and restart this calculation. So we have our x and y value, and we're asked to compute y prime. Again, y prime is given by this equation up here, so that means that y prime is simply equal to y, which is 1.5. Now to find the line. So again, we are at y equals mx plus b. Y in this case is equal to 1.5. M is equal to 1.5, and x is 0.5 plus b. This means that 1.5 equals to 0.75 plus b, meaning that b is equal to 0.75, which means that the line is equivalent to this. So there we go, we have computed our line. Now what we're asked to find is the next x. And again, the next x value is simply the current x value, which is 0.5, plus the step value, which is 0.5, which equals to 1. And as you can see, we have arrived already at what we need to compute, which is y of 1, meaning x equals 1 in this case, right? So what is the y value in this case where x equals 1? Well, all we got to do is plug 1 into this equation right here, and we're going to get a y value of 2.25. And that right here is our approximation using Euler's method for this initial value problem. So that's it for today's lesson on directional fields and Euler's method. Hopefully you guys enjoyed the video and learned something. If the video has helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.